G'day. Well, after, I haven't counted them up, but probably 10 or 12 videos, it's time for us to effect a synthesis. And that is to try to bring it all together and give you some understanding of why polynomials, rational functions, hyperbolae, asymptotes, zeros and all the rest are somehow connected to each other, at least in terms of concept. And here it is. Let's imagine that I had something like x times y equals 0. Well, that's a very simple equation. I think you can tell me that if I have two numbers multiplying to give 0, then either x equals 0 or y equals 0. We have no other alternatives. What's the graph of that look like? Well, we probably don't really need to even label too much on the axis by way of scale. X equals 0 is the y-axis. I'm going to draw this in with a solid line. And y equals 0 is the x-axis. That is our graph. Two intersecting lines. Now I could have chosen lines that were at an angle. I just chose these ones. That is the graph. This, in a sense, is behaving like a polynomial. And I'm looking at zeros, numbers that multiply to give me 0. Now the instant I change this, let's say call it 2, I suddenly change what I'm saying. I have to say that x cannot possibly be 0 and y cannot possibly be 0, so these become asymptotes that the curve is very close to, certainly as you go out towards infinity. And you will know that when we graph this, we get the equation. By the way, I can rearrange this to y equals 2 over x. This is a classic hyperbola. And we'd be finding numbers that multiply to make 2. 1 times 2, 2 times 1. If I go backwards into the negatives, minus 2 times minus 1, minus 1 times minus 2. Oh yes, I'll do it in black. So our hyperbole will look like this. Now, how are we to understand the powerful change, the powerful effect that changing that from a 0 to a 2 had? We've gone from saying that x must be 0 and y must be 0 to saying that x cannot be 0 and y cannot be 0. I'm going to change one little thing and discuss it with you, and hopefully you'll see why it all works. I'm going to change this to a third variable, z. Now to graph this properly with an x-axis, a y-axis and a z-axis, I need to think in 3 dimensions. And I really can't draw a 3-dimensional graph very well. But let's think what is happening. If I multiply two numbers to get z, then here's my xy plane. If I multiply 0 by 0, the z value will be 0. And if we consider the z-axis is the one coming out of the board in the third dimension, so we've got horizontal will be the first dimension, vertical with the next, and then out of the board will be the third, then our point will be right there. In fact, as long as x is 0, I don't care what y is. Z will always be 0 if x is 0. So all along this line, the z value will be 0. Similarly, if y is 0, I don't care what x is. 0 times anything will give me a 0 for z. So anywhere where the y value is 0 along here, the z value is also 0. So we've established that whatever z is doing, we haven't worked out what it's doing elsewhere, but whatever it's doing on the axis, it's worth 0. So in other words, it's on the board. I don't want to mess up my purple pens, but I could go over this in purple. What's it doing in here? Well, let's work out x times y. If x is worth 2 and y is worth 2, what's 2 times 2? Oh, it's 4. So we would have to come 1, 2, 3, 4 units out from the board. What if we had 1 times 1? We'd have to come 1 unit up. If I had 4 times 3, we would have to come 12 units up from the board. In fact, as long as x is positive and y is positive up in here, when I multiply two positive numbers together, I'm going to get a positive value for z. And the bigger x is and the bigger y is, so the more the numbers are out in here, the bigger z is. And in fact, what I get is if I could actually plot the z plane or surface in 3 dimensions, it would be at 0 here and 0 here, so it would actually lie on the whiteboard, and then it would raise up and go down to 0 here. So I'd be looking at part of a curve. In fact, you can consider it as part of a cone or something similar. Does that make sense? Similarly, all the negative numbers, negative x's and negative y values, multiplying the two negatives, a negative times a negative will give me a positive z. So all the z values will be up off the board, be 0 here and 0 here, and I'd see a surface coming up like this. So if you can imagine a surface here and a surface rising up here, what's happening in the second and the fourth quadrants? Well, here I've got a negative x value, -1, -2, -3 and so forth, and a positive y value, and a negative x times a positive y will give you a negative z. So all these values go in behind the board. So I've got a curve coming up here, going down there, and then scooping down behind the board, coming up through this point, over, and yes, in here it'll go down through here and scoop behind the board and come up through here again. So I've got a kind of a wavy pattern going around. And what happens is this: when z equals 0, I've got these two lines where z is actually equal to 0. If I put z equals 1, the question I'm asking is, if I come 1 unit up from the board, up the z-axis, where is that going to cut these curves? In fact, I think we used z equals 2, didn't we? When we had z equals 2, it says if I came up 1, 2 units, these are the contours of where this arc is cut. It's like I wish I could draw this properly. I wish I could animate it. I don't have the software to do it. But if we could imagine this is like a bit of a cone rising up, and it's just been sliced off and sliced off. That's it. And you can now understand why when I increase these values, 2, 3, 4, 5, 6, we're coming z equals 2, 3, 4, 5, 6, and we're cutting this surface further out and just seeing the curves further out. If I put z equals minus something, then I'm trying to move the plane back behind the whiteboard 1, 2, 3 units back, and it's going to cut the bits that scoop, and we're going to see curves back in here and here, which is exactly what we see when we see an equation like xy equals -3. So in other words, if we replace the constant with a z and think in terms of surfaces, now this is a bit of a challenge for you perhaps, we can understand what's happening. Similarly, if I now duplicate one of the asymptotes, as it were, how does that affect the z value? Well, let's go back to z and think about it. It's a bit like when we had when we're graphing a polynomial like this and we duplicated the x equals 2, 0, and here we've got 1 at minus 1. I think this is what I used in the previous example. Instead of the curve going through that 0, by duplicating it, it bounces off and then it goes back down through the next 0. Similarly, by duplicating this 0, if you like, for the z axis, this curve comes over here, but instead of diving through and scooping behind the board, it now bounces off the axis and comes up and gives me another dome up here. So it's scoop, bounce, scoop, then it dives below, messing up my board here. So I'll now put my purple lines up this way. So it's up and bounces off and up and down. It scoops below, it comes up to hit the y-axis, and because x equals 0, which is the y-axis, is duplicated, it bounces back down and it scoops. So we now have a raised area and a raised area and a scoop and a scoop. So bounce, bounce, scoop behind, up to 0 and scoop behind and up. So if I replace the z with a number like 3, I'm really saying when I scoop up here, well not scoop, but when I raise up here and raise up here, if I move up to z equals 3 on the plane, where does it cut these two raised bits? And the answer would be in a curve like that and a curve like that. The fact is that when we're graphing something like a polynomial, to find out where the zeros are and how they behave, we set this equal to 0. That's how we find zeros. And that will guarantee that we have values in certain locations. Now if I start changing values, we find that we have x equals 2, and we have y equals -1. Actually, I should put solid lines there because that's the graph. That's this graph. And this graph's, the x equals 2 is there twice. But the instant I change that to some other number, I'm now saying these are asymptotes. They can't possibly be part of the graph. I'm finding it hard to explain. I love students to experiment when I'm in the classroom and for me to go and discuss with them. That's something I can't do over a video. But I will draw up another example and we'll hopefully be able to analyse it in a way that makes sense to you. Let's look at this equation. Y squared minus x squared, or plus x squared minus 4, times y minus x, y plus x, equals 0. Because it equals 0, we're going to look for what we call zeros, and we're going to think the same way we think about polynomials. And we've drawn this graph before. I find this a good one to discuss principles of graphing. And what asymptote? Well, they're not asymptotes, they're zeros. So in other words, to make this 0, if this was 0, why would we be worth minus x? So, oh, that should have gone through the origin. There we go. Sorry, that doesn't rub out very well. There's y equals minus x. To make this term 0, y would equal plus x. There we go. And to make this term 0, y squared plus x squared minus 4 would equal 0. So y squared plus x squared, or x squared plus y squared, would equal 4. And it would give me a circle of radius 2. That is the graph that this produces. Now, it's unlike anything you're likely to have produced in school, but you can see that by adding more and more terms, you can create extra lines and things anywhere on the surface, on the plane. If I wanted, for example, a little circle of radius 1 up here at 4, what's that circle look like? Well, that circle would be x squared plus y minus 4 squared equals 1 squared. There's my pattern for the circle. The radius is 1, and by altering the y value by 4, you can see that y equals 4 will be the centre of that circle. So that circle is this. So if I rearrange that to x squared plus y minus 4 squared minus 1 is 0, and put that up here, I'll see if I can just squeeze it in. X squared plus y minus 4 squared minus 1. There it is. Having put that in, now adds that little circle there. And you can use all the graphs that you know, hyperbolae, exponential graphs, logarithmic graphs, sine, cosine, tangent graphs, parabolas, cubics, all sorts of polynomials, and build them up as separate terms in here, all equal to 0, and you can have an amazing amalgam of, or collage if you like, of graphs. You can make ellipses with little eyes in and a mouth and so on, and it's using this exact principle that I showed in previous videos, how to actually write I love you or will you marry me with one equation. And you might like to go back and look at those videos. But believe it or not, one equation, in fact it was too complicated for Wolfram Alpha to be able to graph. But I assure you that the equation works. But there are the principles. Now, we'll leave that there. What happens if we change this number to a 1, 2, 3, 4 or 5, or some other number? Suddenly, none of these can be 0, because 0 times whatever's left will not give me a 5. So suddenly the logic's changed. We're not thinking polynomials anymore, we're thinking asymptotes. If this cannot possibly be 0, then y can't be equal to minus x. One of the advantages of a whiteboard, I can now change that to a dashed line. This means that y can't equal x. I now have an asymptote. This means that x squared plus y squared can no longer equal 4, because if they did, that would be 0, and 0 times this would be 0, not 5. So as long as x squared plus y squared equals 4, whatever they make, they're not going to be a solution to this equation. So this is now, in effect, behaving like an asymptote, even though it's strictly not, because it's a closed curve. And this little portion up here, the same thing applies. So now I've got a rather peculiar setup, where I'm told that wherever this graph is, it cannot touch those lines. Now, I told you about the synthesis, imagining that this was Z and looking at the surface. Now, with big Y values and big X values in here, for example, the Z value is going to be quite large. So I'm expecting to see a curved surface up here. Now, it's going to dive down through, this is where Z would be equal to 0, so I've got a little pit or a little depression inside that circle, but I've got a dome outside, sort of pushing down into there. it reaches 0 here and it scoops down below and comes up here and raises up and dives down and scoops behind here. So if I got my, actually I'll get my green pen. Let's put some signs in. So the surface is going to be positive here, negative all out here, positive in here, and then dive back behind and be all a negative scooped out area here. It'll come up to 0 here and be a dome there, so I'll put little pluses in here. This domed area will dive down through 0 and scoop there, and dive down through 0 and scoop here, so this will all be negative. Rise up, positive, positive, negative, negative, and you can see that in every case, because these are normal asymptotes, a negative surface is bounded by positive surfaces, and a positive surface, like this one, is bounded by negative surfaces. In other words, wherever these boundaries are, the surface is coming up through them from negative to positive, or going from positive down to negative. Well, if I want to know where +5 is, if I come up 5 units into these domed areas and cut them, what am I going to get? Well, I'll do it in, here we go, I'll do it in purple. I think you can see that cutting this domed area is certainly going to be here like that. But remember, this domed area didn't just come up like this, it actually dived down and had a little pit or a depression going behind the whiteboard in here. So as it dived down towards here, I'd be expecting to see another contour as it's diving down. Now, where is another positive surface? Here it's up again. There's no little pit for it, so it would be a total dome, and I would expect to see this here. Sorry, it's meant to go closer to the asymptote. I've got a positive region here, so I would expect to see a contour there, and I've got a positive region here. I expect to see a contour there. Well, now we've got something that looks a little bit like a person. A head, a bit of an abdomen and arms and legs. And that's all from this equation, and it's quite accidental. I had no intention of doing that when we started. But there it is. Equal to 0, we're thinking zeros, and we're thinking the way we think about polynomials. Equal to a constant, we've now created asymptotes. And in effect, we're thinking contour lines of three-dimensional surfaces. That is the sort of synthetic thinking that I wanted you to engage in. I encourage you to type in things like that into Wolfram Alpha. Oh, I'll just put it up on the board. I really encourage you to go there. And if you think you'll visit a lot, then the subscription's not that expensive, and I encourage you to subscribe and really play around. You'll learn a lot about graphing. There it is. That's the end of quite a long journey. There's more we could do, but I think for school and early university level graphing, this is quite sufficient conceptually. Getting down to the nitty-gritty of locating points and approximating positions and so on is something else we'll talk about in other series, because some of it will involve approximation methods and calculus and things like that. It's not part of what I wanted to share with you in this series. I wanted concept, ideas. So there it is. Thank you for watching, and please leave your comments and like the video and subscribe. I look forward to seeing you in other videos.